Hi, this is Mr. Upjohn, and we're going to do some math. So we're looking at modeling with quadratic functions. What that means, to everyone's delight, we're doing word problems. And they're not really that difficult. So we got one here. The graphic shows the heights of a supply package dropped from a helicopter hovering above the ground. Would a linear function be a good model for the data? Remember, linear has a constant rate of change. Also, between each thing, it's not the same kind of slope. Would a quadratic function be a good model? Probably not. The quadratic's going to go up and then down, and this just goes down. So what we're actually dealing with here, this would be the graph if we plotted those points. It kind of looks like a line, but then it curves. So not linear. And then we can fill out this table like we did the first day. We plug in our x values. Oh no, we don't even need to plug them in. They gave us the y values. And we find our differences. The first differences, not the same. The second differences, not the same. So it's not linear or quadratic because linear would have had the first differences be the same. Quadratic would have the second differences be the same. And none of that's true. So it's not a quadratic, not a linear, so forget you, package. All right, there's going to be two types of problems we're going to deal with in 3.4, area and vertical motion. So we have this company who wants a rectangular pool with the dimensions shown. I don't know if we can read this. That is 4 feet. That's x. And that's 2x. If Carolina wants a 15-foot wide pool with a deck, how many square feet will she need to have available in her yard? So again, that we're finding our area because that's our square feet, how she needs for a yard, width and length. So another thing, oh no, I guess we did write it. So this border, this deck is 4 feet all around. So 4 here, 4 here, 4 here, 4 here. So we have those extra measurements. Write a quadratic function to represent the area of the pool and the deck. So we want the whole rectangle, including the deck. Well, from here to here of the pool is 2x. But that's not what we want. We want to include the deck. Well, that means we would add 4 and add another 4 because we have the deck extending at 4 feet on both sides. So that's how we're getting 2x plus 8. Now, very similarly, if we look at this dimension, again, just of the pool, it's x. And we're going up and down. Well, we got to add the deck on, and of course, it's still just 4 plus another 4. So x plus 8. So that expression is what we're going to use to find our area. So the way we find that area is length times width. We've seen that before. And we just multiply those two polynomials. So 2x plus 8 and x plus 8. So you can do FOIL, the vertical method, horizontal method, box, double distribution, anything you can think of. Just as long as when you multiply, you have 4 terms. So 2x times x is 2x squared. 2x times 8 is a positive 16x. Now 8 times both of those. 8 times x, of course, is just 8x. And then 8 times 8 is 64. Now, of course, we can combine these two to get 24x. And that's what they got. So that is a representation to find the area of the pool and the deck. So together. Now, letter B, find the area of the pool and the deck. Well, she wants a 15-foot wide pool. So that is our x. It said our x was, or our width is x. So you just plug in 15. F of 15, or f of x, is the area. X is the width of the pool. So we substitute it in. I'm going to rewrite it down here because they kind of skip some steps. I don't want us to lead us astray. So we're just plugging in 15 for x into what we got in part A. So we have 15 squared, so that's 225 times 2, 450. We have 24 times 15, which is 360. And of course, we just have that 64 chilling by itself. So we add those up, and we get the area we need. So Carolina needs 874 feet squared. Make sure you have your units and correct units to build a 15-foot wide pool with deck. So again, that's our area kind of problems. They'll give you the width or the length, or at least one way to find it, and you multiply them together. So the other type of problem we're going to look at is vertical motion. Now, all this is an equation for finding the height of something after a certain amount of time. So it's h of t. So h is the height. So h of t is the height at t seconds. And t is, well, the seconds. It's for time. So we have, I've already talked about h and h of t. T is our seconds. V naught. So the way we say it, V naught. Not N-O-T, but naught. Same thing with H naught. Again, same type of thing. So what they are, V naught is the initial velocity. All that means is how fast you're going when you start. And they'll give you that, you just kind of plug it in. H naught is the initial height. So we start at that original height. So again, this is what we want to make sure we can do. Plug in those values, and we go on. So we have a model of vertical motion. Now it's pretty clear that this is a quadratic. We went up, and then we went down. That's a quadratic. Did we go up all the way from the ground? No, because he can't fly. So he's already up there. So a diver jumps off a high platform at initial vertical velocity of 16 feet per second. So pretty quick. So that will be our, oops, not that one. Our V naught. That's our initial velocity. That's how fast he was going when he started. Then, well, what quadratic function represents the height h of the diver after t seconds? Well, we almost have our equation. Again, we want that. Now, again, our initial velocity, V naught, is 16. So 16 goes in front of the t here. It's just substitution. Then we need to have the initial height. Well, the initial height is 30 feet. So we're up on that high platform. So we have our equation, negative 16 squared, and that's always going to be negative 16. Negative 16 is kind of taken into consideration for gravity. We don't need to know all that, though. So how many feet above the platform will the diver be at the highest point of his dive? So, again, h is the height, and that's kind of like our y, or f of x, and t is our seconds, or our x. So those are, so we can relate it back to things we've already done. So how many feet above the platform will the diver be at the highest point? So the highest point, and we got an upside down parabola, so the vertex is the highest point. We get an ordered pair, which gives us our time, x, and y, height of our vertex. So again, if it's in standard form like it is, you do your t equals negative b over 2a, just like we did in class. So a is negative 16, b is 16, c is 30. So we just plug them in. So it's negative 16 over 2 times negative 16. That all simplifies down to 1/2. The negatives cancel out, the 16s cancel out, and that's why we have 1/2. So that is our x, or our t, so time. That means at half a second, this diver is high as he's going to get. That is the highest point. Now, what is the highest point? How high? Well, we have to plug that 1/2 back in. Again, just like how we find our y for the vertex. So we plug in 1/2. We simplify it using our order of operations. So 1/2 squared first, then times negative 16, then 16 times 1/2, and then add them all up. So we get 34 when we simplify that. So our vertex is 1/2 comma 34. Again, just like we did in class, nothing too different. However, the question asked, how many feet above the platform will he be at the highest point? So a little bit different than probably most problems we're going to see. But at 1/2 second, he is 34 feet high. And again, this is the highest point he's going to get. So 34 feet is really what we're looking for, the highest point of the dive. However, again, it says above the platform. Well, the platform is 30 feet up. So the difference between those two is just 4 feet. He jumped up 4 feet by the time that he started falling down or diving down into the pool. And that's what they all say right here. So you're going to have these vertical motion problems, and you're going to have your area problems. So again, just in summary, again, the two types of problems. When the length and width of a rectangle are each variable expressions. Again, that's these because they have an x in them. That's a variable expression. The quadratic function can be used to model the rectangle's area. Because it's length times width, we just multiply the length and the width, which in this case, I guess we'll make this width, this length. So we got 3x plus 4 times x minus 2. Again, we need to multiply those. So this time I'll use the box just to mix it up a little bit. So 3x times x is 3x squared. 4 times x is 4x. 3x times negative 2 is negative 6x. And 4 times negative 2 is a negative 8. So of course we can combine our like terms here. So we get, well, what it says right here. So that would be a model to show the area of that rectangle. And then our vertical motion, again, v naught is the initial velocity, how fast we're going when we first jump or shoot something in the air or whatever. H naught is the initial height. Again, t is seconds. H is our height. And so, again, h of t is the height. Again, that's h. Is the height at t seconds. So you can see his height at any number of seconds. You just plug it in. However, depending on how high you were, that height might be negative and you can't go into negative. So there you go.